Hello, this is Glenn Porter, and today's lecture is on pixel or bit depth. So the agenda today in this lecture is to talk you through the concept of pixel depth. So we're going to have a look at this definition and describe what bit depth means. We're also going to look at different image modes like bi-level, grayscale, RGB, and CMYK. Now, a couple of things to get used to regarding computer jargon. I'm not a computer boffin, but the difference between bit or byte. A bit is a single unit of computer information, and that single unit is a binary unit, which it means that it's either on or off or represented numerically as 0 and 1. A byte comprises of 8 bits. But to be honest, we don't really need to know that for this concept. You may be already familiar with the concept of the way we describe file sizes, how much information is actually stored in that file, and that's expressed in bytes. So kilobytes, kilo meaning 1,000, so 50 kilobytes is 50,000 kilo or 50,000 bytes. Megabytes is another way of describing file size. So kilo is 1,000, mega is 1,000 times 1,000 or 1,000 square. Gigabytes is 1,000 cube, 1,000 times 1,000 times 1,000, and terabytes is 1,000 to the power of 4. So 1,000 times 1,000 times 1,000 times 1,000. So terabytes is very large file sizes, whereas kilobytes are the smaller ones. So kilo, mega, giga, tera are ways of describing the volume of how many thousands of bytes are actually, or millions or billions of bytes are actually in those files. So bit depth and pixel depth mean the same thing. If you're reading literature that describes it as pixel depth, but you know it as bit depth, it's actually exactly the same terminology. And pixel depth allows each pixel. So remember, on our sensor, sensors are divided up into millions of small picture elements called pixels. And it's those pixels that actually reproduce the image. So pixel depth defines actually how many variations of tone or shades of color that pixel has the capacity to reproduce. So the tonal range or the color fidelity of your image is limited by the bit depth or pixel depth. We'll unpack that in the next few slides. The bit depth options that we have are 1, 2, 4, 8, 10, 12, 14, 16, 24, 32, 48, and so on. Probably the most obvious application of bit depth is in our RAW format or our RAW capture. The camera's capacity to record tonal values is defined in this bit depth. And when we're shooting RAW files, depending upon the camera manufacturer, but we're generally shooting between 12 or 14 bit, most likely 14 bit in most modern digital SLR cameras. When we process that RAW file, we generally process it 16-bit, even though it's kind of 14-bit really. Now, one of the interesting differences between JPEG and RAW is actually the bit depth or the pixel depth. When we're shooting at RAW, we're shooting around that 14-bit, close to 16-bit capacity, which gives us a much greater tonal range than JPEG because JPEG is processed at 8-bit. So JPEG files are 8-bit files. RAW files are usually 16-bit, although they're more likely really 14-bit. But we certainly process them at 16-bit. So the difference, this is one of the main differences between shooting JPEG and RAW, and that's why professionals shoot RAW, is the amount of pixel depth you get, the extra pixel depth you get from the bit depth of the camera. So those pixels have a much greater variation, which means a much greater tonal range in the initial capture of the image. So that's why we always recommend you shoot RAW format, never JPEG, unless it's party shots or shots that you're only going to print up as 6x4s. You're not going to do much more. Or 6x4s are postcard size photos. So bit depth is really important in that capture mode, but let's have a look at what it means in the sense of an image. So remember, a bit represents the single unit of a binary code or a computer unit, which is 0 and 1, on or off. Bitmap and bi-level images are usually 1-bit images. Now they're called 1-bit, and the way you write this numerically is 2. So 2 represents the two different options, 0, 1, on, off, and to the power of 1. So 2 times 1 equals 2. So you get two different options. So in that computer code, each pixel really only has a choice of, because you're only using one single sort of unit, it only has a choice of either it being a 0 or being a 1. So in that, if you think of that pixel, that just means it can only either be black or white. Can't be grey, can't be blue, can't be red, can't be any other tone except for black or white, because it's a 1-bit image. It can only be one or the other. It can only be a 0, on, or a 1, which is off. Now 1-bit images are characteristic of what we call line copy. So black and white images that are just black or white. When we're looking at text on a white page, that is a bitmap bi-level type image. We have our white background in the paper and the black text, so it's black and white. So a 1-bit image is a line copy image, and it only consists of two different variations at the pixels. Okay, now in a 2-bit bit depth or pixel depth, we have 2 bits now, so we have 2 to the power of 2. So 2 times 2 equals 4. So we have now 4 different variations that pixel can actually reproduce tone. It can reproduce tone as a 0, 1, a 1, 0, a 0, 0, and a 1, 1. So you can see on the screen there those 4 options on the 4th bullet point. So it can only be, so the pixel can only be one of those things because it doesn't have any more code to interpolate the pixel. The computer code is very low in resolution in the sense that it's only 2 bits. So we only have 4 variations of tone. Those 4 variations can be seen on the screen. So we've got black, grey, lighter grey, and white. They're the only 4 options that one single pixel can produce in a 2-bit image. Okay, so let's step it up now to 8-bit. Now the interesting thing about 8-bit or 2-bit and 1-bit is not what we would call photographic quality. We can't reproduce what we call a continuous tone print. Continuous tone print is a concept that we associate with traditional black and white photographs. So it's a continuous tone, meaning that there are so many different variations of grey or variation between white and black that the variations seem to be continuous. There's not any sort of segments of tone. It becomes a nice even blend, and that's what we call photographic quality or a continuous tone print. For digital, because digital files and digital images are made up of little square mosaic pixels, we have to have a bit depth that also has or responds or has enough variation to appear to be a continuous tone print. So the minimum photographic quality of a digital image is a 8-bit image. And an 8-bit image, 2 to the power of 8, which equals 2 times 2, let me start again, 2 times 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 2, which equals 256. So 8 lots of 2, multiply them together, as you can see on the bottom there, represents 256 different shades of grey. Now that's because in the previous 2-bit image, we only had 4 different options. Well, now we have 8 bits of information, 8 lots of zeros and ones. 8 lots of zeros and ones, and all the different combinations of 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. If you look at all those different combinations, there's actually 256 different combinations when you combine 0 and 1 with 8 numerals. What's interesting about 8-bit, it's considered to be the minimum level to produce continuous tone print. So we're now into the photographic quality, whereas before we were in just line copy or very crude sort of reproduction of image with only 4 tones. So an 8-bit image has the concept of 256 shades or tone variations within each pixel. Now, this number should sort of be familiar to you. There's something familiar should appear with this number of 256. Because when we're looking at our histogram, if you remember from last semester, we had 0 to 255 amount of grey values on our histogram. You remember when we look at the histogram, we had a 0, which was black, 255, which was white, and then we had all those variations in between. Well, that's actually 256 different shades because 0 is actually a value. So when you include 0 as a value and 255 up to 255, that actually equals 256 different values or different shades of grey or colour. So what we can see at the bottom there is this concept of 256 shades. So it becomes a continuous tone grayscale, even though it's not really, because each pixel has a defined value. So there is some sort of segments between each of those values, but because our eyes can't see that change of values, it appears to be a continuous tone. Now, if we revert to a color image, now remember, color images now, RGB images, red, green, blue, there's actually 3 channels. There's a red channel, a green channel, and a blue channel. So when we have an 8-bit RGB color image, we get a continuous tone color image. So now we have, within our red channel, we have 256 shades of red. In our green channel, we have 256 shades or variations of green. And in the blue channel, 256 shades or variation of blue. When we combine those 3 colors to produce a full color image, we get 256 times 256 times 256, which equals over 16 million colors. So theoretically, not practically, but theoretically, our 8-bit RGB images have 16 million different colors. Now, another way of looking at an 8-bit, usually we say 8-bit RGB. When we're shooting in color JPEG, we say it's an 8-bit file. But really, it really is a 24-bit file, because we're using 3 channels at 8-bit, so 3 times 8 equals 24. So whether you describe it as an 8-bit RGB, we know what's meant by that. It's actually 8 bits per channel, which equals 24 bits. Okay, so 8-bit is one of those, it's the minimum standard to produce a continuous tone print. In color, because we have 3 channels, we need 3 lots of 8 bits to produce a continuous tone color image. That gives us 16 million different colors. So we've gone from 256 different shades in the grayscale on an 8-bit grayscale image, now to 16 million variations of color. This sort of maps out those 3 differences that we've talked about at the moment. So a 1-bit file, we just have a black and white option, so a line copy. So either it's black or it's white. In the 8-bit grayscale, we now have, which is our continuous tone grayscale, we have our normal type of black and white image. In an 8-bit RGB, 24-bit color, we now have a full color image with 8 bits per channel. So in an 8-bit per channel RGB file or a 24-bit image, each pixel had the capacity, in a theoretical sense, of 16 million variations. However, what happens if we went to 16-bit per channel, like what we produce when we're shooting in RAW file, color RAW files? Not quite 16-bit, 14-bit. Yeah, okay, I get that. But let's just for clarity's sake say it's 16-bit. So what 16-bit represents, rather than 256 different shades, 16-bit represents 65,536 variations of tone in each pixel. So when we've got 3 channels at 16-bit, we've got 65,000 times 65,000 times 65,000, which actually ends up being billions of colors. Now, practically that's impossible because we have to come back to inks and light on a screen, so we can't actually physically produce that. But theoretically, in our file, in our digital file, each pixel has the capacity at 16-bit per channel to produce billions of different tonal variations. So as you can see, when you increase the bit depth, you get more tonal range within your image. Why is this important? It's really important because we'll explain this a little bit later on in the next lecture. But I'll give you a little secret before the next lecture. Tonal range is the key to quality. It's not sharpness, it's not resolution, it's not processing. Tonal range is the key element to print quality. Now 48-bit CMYK, you might see this on some scanners and some so forth, not so much cameras. But CMYK is another image mode that's used in the graphic arts industry. So graphic reproduction in magazines and brochures and books and so forth use CMYK images rather than RGB. In actual fact, when you send your RGB color image to a digital printer, the printers, if you look at the inks, they're not red, green and blue. They're actually cyan, yellow, magenta and black, and very different variations of those. It might be 2 magentas, might be 3 blacks and so forth. But CMYK, K means black, you have now 4 channels, not 3 channels. So in a 48-bit CMYK image, rather than being 16-bit per channel, it's actually 12-bit per channel. So that's it for the definition of pixel depth. It'll probably make more practical sense when we're talking about dynamic range of the cameras in dynamic range lecture. But the important thing is to know that really pixel depth is about the ability of that single pixel to record variation of tone. So the greater the pixel depth, the greater that pixel has in producing different variations. The greater the variation, the better the tonal range and color fidelity. So that's why pixel depth is important, and that's why as professional photographers we like to shoot in RAW to get as much color fidelity or tonal range as we can at the capture stage. So I hope that makes sense, and thanks for listening, and I'll talk to you soon. Bye-bye.